Hey everybody, welcome to our first video on Unit 4, which is all about the mole. So we're not talking about the animal, the mole, and we're not talking about this kind of mole, but we're talking about a chemistry type of mole, which is a little bit different from the mole that you're probably used to hearing about. So you recently did the size of an atom lab, and you had a piece of galvanized metal, and galvanized means it's coated with zinc. And you were able to calculate the number of layers of zinc that you took off of that piece of metal. And you probably had over 20,000 layers. I think, in fact, most students get above 30,000 layers. 30,000 layers of zinc you took off of each side of that piece of metal. And when you compare that to the width of a sheet of paper, so I happen to just have the notes here. If you compare that to this width, or this height, I should say, of a piece of paper, those 30,000 layers is about 1/10 the height of a piece of paper. So imagine taking this through a deli slicer and cutting a sheet of paper into 10 more ways in this direction. That's about how tall 30,000 atoms of zinc was on the top of that piece of metal. So atoms are really, really, really small. And therefore, we need to have a way to measure a very large number in chemistry. Because atoms are so small, we need a measure that's very large to represent them. And that's what a mole is. So a mole is a unit of measurement that tells us how many particles are in a certain unit. However, for a mole, we say that 1 mole of something contains Avogadro's number of particles or things. And Avogadro's number is 6.02 times 10 to the 23rd. So 1 mole of something contains 6.02 times 10 to the 23rd of that thing. It's a representation of the quantity of something. And I always like to relate this to donuts, because who doesn't like donuts? So when you go to Dunkin' Donuts, you say, I'll have a dozen donuts. And they know exactly what you're talking about. So 1 dozen is equal to 12. That's a word that we use to represent the number 12. And there's a lot of words that we have numerical values to. A ream is 500. We say a couple is 2. There's a lot more than that, but those are just the first 2 that came to my head first. Therefore, because a mole is the same kind of measurement, if a dozen is 12, a mole is just 6.02 times 10 to the 23rd. It's that many things. The only reason why that number is so big in comparison to 12 is because atoms are so small, which you saw in that lab that you recently did. So we need a very big number to represent them. So of course, 6.02 times 10 to the 23rd is a huge number, and it's very difficult to think about really how big that number is. But that's something that we're going to work with as we progress through this unit as well. So let's say you go to Dunkin' Donuts and you order a dozen glazed donuts and you order a dozen Boston cream filled donuts. You have 12 of each of them, right? Because that's what a dozen is. You have 12 glazed and you have 12 Boston cream. So you have both of those dozen in your hands. You have one in this hand and one in this hand. However, although you have the same number of each of those donuts, the mass of those dozen each is going to be very different. The mass of a dozen glazed donuts is not the same as the mass of a dozen Boston cream filled donuts. Why? Because a glazed donut and a Boston cream filled donut aren't made up of the same things. A Boston cream filled donut has that creamy center with the chocolate on top. A glazed donut doesn't even have a center, right? And usually it's a lot fluffier. So same number of each of them, but a different mass. And elements are the same way. You can have the same number of atoms of 2 elements, but they're going to have different masses, and that's because they are different elements. They all have a different number of protons, neutrons, and electrons. So let's consider this. I have 1 mole of the element carbon, and I have 1 mole of the element bismuth, two of my favorite elements. Again, where 1 mole is just representing the quantity of something. Because atoms are so small, we have to have a huge number to represent that. So 1 mole of carbon, of course, would equal 6.02 times 10 to the 23rd atoms of carbon. And 1 mole of bismuth would represent 6.02 times 10 to the 23rd atoms of bismuth. So you have the same number of those atoms because that's what a mole is. 6.02 times 10 to the 23rd atoms of carbon, 6.02 times 10 to the 23rd atoms of bismuth. Same number of each of them, but the mass of 1 mole of carbon is going to be different from the mass of 1 mole of bismuth. If you look on a periodic table, carbon's atomic number is 6, which means it has 6 protons in the nucleus, whereas bismuth has 83 protons in the nucleus. Just think about mass number, what we talked about in the last unit. The protons themselves contribute to the mass number. So because bismuth has 83 protons in its nucleus and carbon has 6, the mass of 1 mole of bismuth is going to be quite a bit heavier than the mass of 1 mole of carbon. And again, that's because a mole has the same number of particles. 6.02 times 10 to the 23rd. We call that Avogadro's number. It's the guy who came up with this idea. And the value that we use to represent the mass of 1 mole of a substance is the molar mass. Now, you're familiar with the molar mass because I don't know why, but chemists like to have like 5 different names for the same exact number. The molar mass is the same as the atomic weight, which you just finished calculating in Unit 3, actually. So you could find the mass per 1 mole of an element, or its molar mass, right on the periodic table. That's its atomic weight. So here's carbon's little square that you'd find on the periodic table in addition to bismuth's. And of course you have the name, you have the atomic number, but you also have the atomic weight. This is also called the molar mass. So that means that 1 mole of that element has a mass of whatever this value is. So for carbon, 1 mole of carbon has a mass of 12.011 grams, whereas 1 mole of bismuth has a mass of 208.98 grams. Again, where both of those represent 6.02 times 10 to the 23rd particles. That's what a mole is, 6.02 times 10 to the 23rd. Is that number ingrained in your head yet? Because it's going to be ingrained in your head very, very soon because you're going to hear me say it a lot. So therefore, we say carbon's molar mass is 12.011 grams per mole, grams per 1 mole. You're familiar at this point with the units of this being AMU. Not only can you use the units AMU, atomic mass units, you can also use grams per 1 mole. And bismuth's molar mass, therefore, is also grams per 1 mole. In your notes, you have this really nice kind of chart, I guess, that tells you how to convert between the number of grams of something to the number of moles of a substance to the number of particles. Now, I'm not going to take you through this right now because I just like to show you how to do the calculations rather than talk about how to do the calculations. I think it's easier to do them than it is to talk about how to do them. So we're just going to dive right in actually and do sample problem 1 together. We're not going to do all of them, but I'd like for us to do some of them. And then we'll get some more practice with those in class next time I see you. This is the point at which dimensional analysis becomes important again. So you needed to know how to use dimensional analysis back in Unit 1 because now it becomes important. Now we're not that familiar with these units. You cannot just move the decimal point over. You need to understand the process of dimensional analysis. And that's why we did so much practice with that back in Unit 1. So it wasn't just to make your lives miserable, but it's a crucial skill. And chemists need to know how to do dimensional analysis. The fun thing, you probably don't think it's fun, but about chemistry is that everything builds on each other. So we can't forget the old stuff we used to do because we're probably going to need to use it when we do some of this new stuff. Anyway, I'm rambling. Let's jump right into sample problem 1. So let's go ahead and do these next sample problems together. We're not going to do every single one, but I would like for us to do at least most of them, all of the one-step problems. So I have a new little setup over here, which is kind of interesting. My sister gave me this like pad I can write on, and it goes right on the screen, so that's cool. What is the mass in grams of 3.50 moles of carbon? Of course, just like if you were doing dimensional analysis, you do want to write down what you want to convert first. So we are going to convert 3.50 moles of carbon. And we're going to set up our crosshair, put a 1 underneath like you normally would when you were doing dimensional analysis. And then whatever units up top, we're going to bring that down. Moles of carbon, and we want to convert this to grams of carbon up on the top. So before we do this, we need to figure out what's the relationship between moles to grams. And really, we have 2 options. And let's change the color here. So one of the options that we could use, let's try one of these effects, that sounds different, is the molar mass. And molar mass is what you find on the periodic table. And the molar mass on the periodic table is always given to us in units of grams per mole. So it's the number of grams that's equivalent to 1 mole of a substance. That's one of our options we can use to convert. The other option is Avogadro's number. Avogadro's number. And Avogadro's number says that 1 mole of anything is equivalent to 6.02 times 10 to the 23rd of those things. So basically it's the number of particles, however many particles or how many things are comprising 1 mole of a material. So what equity do we need to use? Well, we need to use the molar mass, and that's because we're relating the number of grams to the number of moles. Let's go ahead and erase that line there. So you look on a periodic table, and carbon's molar mass is 12.01. That means that 1 mole of carbon has a mass of 12.01 grams. So we need to make sure we plug these in next to the correct unit. So see how there's a number 1 next to moles? That number 1 needs to go next to 1 mole in my conversion factor. Let's actually highlight that so we could see. This 1 mole and that 1 mole has to be the same number. And therefore, your number on top is going to be this 12.01. And that's because 12.01 grams is equivalent to 1 mole. So notice how I have those next to the correct units as well. 12.01 grams is equal to 1 mole. And of course, you could cross out your units that way. Then you would just multiply these 2 numbers because they're both on top. And to the correct number of significant figures, your answer should be 42 grams of carbon. Just like that. Let's try B. What is the mass in grams of 2.25 moles of iron? So 2.25 moles of iron. We want to know how many grams is this. So again, whatever units up top, let's bring that down. Moles of iron to grams of iron. And you don't have to write the symbol, although I sometimes like to, just because it keeps everything nice and organized. Those units cancel from those units there. And again, what's the relationship between grams to moles or moles to grams? Well, again, you're going to use the molar mass. You don't care about the number of individual particles that are given. So therefore, you're going to look on the periodic table again, and you'll find that iron's molar mass is 55.85. That means that 1 mole of iron has a mass of 55.85 grams. And again, where 1 mole is always equal to 6.02 times 10 to the 23rd. Make sure we plug our numbers in next to the correct unit. So here again is my 55.85 grams. So I'm going to plug that in on top. 55.85 grams per every 1 mole. And let's go ahead and just highlight the 1 mole section here. I'm going to do that in green. Per 1 mole. And then of course we multiply again because both of those numbers are on top. So 2.25 times 55.85 to the correct number of significant figures, you should have an answer of 126 grams of iron. Like so. You try C, because C is just like A and B, just with a different element. And I want you to pause this video and then restart it, and you'll see my answer pop up. And the answer for C should be 22.5 grams of potassium. Same exact thing. All you did was you started off with a different number, and then of course a different molar mass because it's a different element. Let's go ahead and try D. So a chemist produced 11.9 grams of aluminum. So we have 11.9 grams of the element aluminum. And we want to know how many moles was this. So a little bit different here, but there might be a lot of segments where it's cut out here only because I'm having a hard time learning how to use this. So it's a little choppy, I think, when I'm typing everything out. But in this case, notice how your units are not set up in the same exact spot. So we do have to work backwards from these previous ones. And that's why it's so important, I think, not to memorize anything in chemistry. You always want to learn the process of how to do it. Because if you know the process and how it works, then really you shouldn't have to second guess any of the answers to your problems because you know what you're doing and how to achieve the correct answer. So let's go ahead and decide, what do I need to use as my conversion factor? Well, we're still relating the grams of aluminum to the number of moles. We still don't care about the number of particles, and therefore we still don't care about Avogadro's number. So we do have to look on a periodic table to find the molar mass of aluminum. And the molar mass for aluminum is 26.98. And it's grams per mole. But again, what does that mean? That means that 1 mole of aluminum has a mass of 26.98 grams. Let's go ahead and plug our numbers in. So again, we need to represent this right here in my dimensional analysis problem correctly. And in order to do that, 1 mole of aluminum has a mass of 26.98 grams of aluminum. So let's go ahead and highlight some of these things again, just so you could see them. 26.98 grams and 26.98 grams is equal to 1 mole, and 1 mole's on top. So that has to be the same. 1 mole, 26.98, 26.98. And in this case, you just have to multiply to get the correct answer. Just make sure your answer is to the correct number of significant figures. Answer should be 0.441 moles of aluminum. I want you to try E and F. So E and F is just like this one. You're still using the molar mass as a conversion factor. Again, pause this video, try both of those, and see if you got the right answer. And there are your final answers for E and F. So again, always just make sure that your answers are represented to the correct number of significant figures. If you have a number that's close, but maybe you have some additional numbers on there, or I have an additional number, just always check those significant figures. Let's try G. So G is a little bit different. How many moles of lead are in 1.72 times 10 to the 22nd atoms of lead? We're going to set up our crosshair just like we did. 1 down below is a placeholder. And in this case, we're going to convert atoms of lead to moles of lead. Now let's go back up here just to look. So we care in this case about the number of atoms. And remember, an atom is a type of particle. So 1 mole of anything contains 6.02 times 10 to the 23rd things. Here, we're going to have to use Avogadro's number as a conversion factor. We don't care about the mass of that sample. So therefore, we don't even have to look on a periodic table to find out what the mass of the sample is. All we need to know is that 1 mole, in this case of atoms, contains 6.02 times 10 to the 23rd atoms. That's it. That's all we have to know how to do. So let's plug these numbers in next to the correct units as well. 1 mole of atoms. So 1 mole of, in this case, lead. 1 mole of lead. Let's go ahead and highlight that. 1 mole of lead contains 6.02 times 10 to the 23rd atoms. 6.02 times 10 to the 23rd atoms. So let's go ahead and highlight this second color here. Let's use this pink. Contains 6.02 times 10 to the 23rd atoms. I think the biggest issue with these is making sure you type these numbers in parentheses. So in your calculator, you need to use parenthesis 1.72 times 10 to the 22nd. Close the parenthesis. Then do a division sign and then a new parenthesis, 6.02 times 10 to the 23rd. Close that parenthesis again. If you don't use parentheses, you're not going to get the correct answer. The calculator is going to do order of operations. So if you are doing this, check your answer with mine. Make sure you're getting the same thing that I'm getting. Your answer should be 0.0286 moles of lead. And again, if you don't get that answer, just double check to make sure how you typed it in the calculator. It should be 1.72 times 10 to the 22nd in parentheses, and then your division sign, and then a new parenthesis, 6.02 times 10 to the 23rd. You try H right now. So one more time, pause this video, just try to do H. Answer to this one is kind of a big round. So the answer is about 415 point something. However, your answer should have only 2 significant figures because that's how many this first number has. And therefore your last value should have 2 significant figures as well. Let's do one more for this video. How many atoms of aluminum are in 2.75 moles of aluminum? Again, one more time, set up the crosshair. Here we go. We'll bring a 1 down here as a placeholder. Moles of aluminum to individual atoms of aluminum. Now notice here again, you don't memorize where numbers go here. Avogadro's number happens to be on the bottom, and that's because this unit of atoms is also on the bottom. Here, atoms is on top. So we have to place Avogadro's number on my numerator in this dimensional analysis problem because 1 mole of aluminum is on the bottom. Again, the conversion factor says that 1 mole of anything contains Avogadro's number of things. 6.02 times 10 to the 23rd things. So 1 mole contains Avogadro's number of things, and 1 mole contains Avogadro's number of things. In both of these cases, the thing is the atom. And then let's just solve. So in this case, 2.75 times 6.02 times 10 to the 23rd. Remember, you do need to use parentheses around any number that has an exponent. You really don't have to for this one. So actually I'm going to erase that just because you don't need to use it there. But you should have, however, used it in this problem up top. Each of those values should be in parentheses. And then of course, this value, Avogadro's number, should also be in parentheses. And your final answer is, let's see, 1.66 times 10 to the 24th atoms of aluminum. And that's it. So everything we just did here are 1-step problems. Now, tomorrow when you come back to class, we're going to do 2-step problems. So we're going to review the 1-step problems, but then you'll do some of these 2-step problems where it says, what's the mass given the number of particles, or what's the number of particles given the mass? Now, if you look back at this over here, you'll see that you always have to convert to the unit of moles. Actually, in chemistry, moles is like the golden unit. You need to use moles all of the time. So let's take that nice gold pen out again, and we're going to highlight this, do something with it. But the moles of a substance is what you always need to find. This relates everything to everything else in chemistry. This is crucial. Mole conversions are very important. If you are converting from the number of grams to the number of moles, you need to use the molar mass as a conversion factor. And that molar mass is what you find on the periodic table. And this nice graph tells you what to do with that molar mass. So if I'm going from grams to the number of moles, you do need to divide by the molar mass. Or if I'm going from moles to grams, you do need to multiply. On the other hand, if you are converting to particles from moles, you do need to use Avogadro's number. And Avogadro's number is that 6.02 times 10 to the 23rd of anything is equal to 1 mole. And of course, if I'm going from moles to particles, you do need to multiply by Avogadro's number. And if you're going the opposite direction, particles to moles, you need to divide. Just another thing before I sign off here, remember that a particle could be a lot of different things. Particles could be atoms. Particles could be molecules. Particles could be formula units. Particles could be unicorns. I mean, it doesn't matter. 1 mole of anything contains 6.02 times 10 to the 23rd things. So don't let any type of particle get you unsure of what you're doing, because 1 mole of anything is always Avogadro's number of things. I hope this video helped. This was the 3rd time I was filming this, so hopefully the writing on the screen was okay, because I think if this works out nice, this might be what I'm doing from now on. If you have any questions, let me know. We will be doing lots of practice with mole conversions as we go throughout. Otherwise, I will see you in the next video. Bye.